another set of natural code. So let's have a big hand for Mark Isaacson.
All right, thank you. So what is the set of natural code? Well, this talk is about compiler and language trends, modern languages, modern compilers, and what they let us do, new things that we couldn't do before, old things that we can now do safer, all of the above. So we're going to start this talk with a brief look at some history. We're going to talk about C and C++, some of the things that are better in a C++ world. And then we're going to carry on in the future, and we're going to look at where is C++ going. And to do that, I'm not going to be listing a bunch of standards proposals. Instead, I'm going to show you the D programming language. Now, you might be wondering, why D? Well, D has done a lot of things now for years. It's had things like ranges. And a lot of these things, again, like ranges, are coming to C++. The ranges proposal is expected to ship in C++ 20. We've got other things like constexpr, which I think is influenced in part by D. So being able to do more and more work at compile time and what that gives us, what new powers we can take advantage of. And all of this is possible because our compilers are so much better than they used to be back in the day. It used to be, when we were talking about the first version of C++, that not only did it take compiler vendors years to catch up with the actual standard, but once they did, it wasn't even fast, right? It just worked. You had the Stepanov abstraction penalty benchmark, which was a benchmark saying, we have all these wonderful new safer primitives in C++, but we pay for them. We pay in our runtime and our compile time to make those things work. Well, long gone are those days. In fact, most of the time, abstractions make things faster, and that'll be a theme that we'll go over in this talk as well. Now, because I'm going to be talking about the D programming language, which I expect nobody in the room has used before, please ask questions. There's going to be syntax up here that is unfamiliar. I'm going to try and explain it. If I forget something, raise a hand. Actually, just curious, has anyone in the room used D before? Show of hands. There we go, non-zero. How about people who have heard of D? Exciting. That's more than what I thought could hope for. So let's dive into our history lesson. If I wanted to write a generic vector-like container in C, one way I might go about that is as follows. I would have a function that created it, a function that freed the memory, and a function to add some elements, and I end up storing this as an opaque pointer, a void star, or maybe a type def to void star. We've got some problems here. That void star can be null. That void star might be my container, but it might be something totally different. I allocate it and then put the element in, which I'll talk about why that, it may not sound that bad, but I'll explain in a second why it is. And of course, I can forget to free my resources. It's so easy to forget to deallocate the memory. Now, this container only works with integers. If I wanted to make it more versatile, to work with any type that I could give to it, I could instead make it so that it accepted void pointers for all the elements. But now I've got indirection and allocations. I could copy paste it. I could do templates, but by hand. All of these solutions, not so great. C++, one line, vector of int, container, give it the initial element that I want to put in there right away. This is good for a few reasons. It's strongly typed. I'm never going to be able to put the wrong thing in. It frees the memory for me automatically as it falls out of scope. And a hidden benefit, it allocates the right size initially. I don't have this guess the size that I'm going to need and then add something in and hope I have enough space, maybe call the allocator again. It's, I know how much space I need, give me that much space right away, first thing. So things are better. Here's another example where I think things are much improved. If I wanted to have a square function or macro in C, things get a little crazy because we don't have overloading, we don't have templates. That's why the absolute value function, you've got abs and fabs. If I want something generic, macros are the only option. They're the only way to do it. And what sucks about macros is that those parentheses, I need them. Without the extra parentheses, if I had just written x times x, it will work some of the time, but not all of the time. I can call it with 2 and it will be correct. Square of 2 is fine. Square of 2 plus 2, on the other hand, falls apart, breaks at runtime, not so great. The template solution in C++, more verbose, yes, harder to make a mistake in. If you make a mistake, you're going to get a compiler error. So just kind of a short history, types make things better. That was, I think, the major kind of increase in our natural language to express ourselves in code between C and C++ is that the type system is so much stronger. Let's talk about D. So D is a systems language. It compiles down to native code. There's no JVM. On top of that, it is statically typed, same as C++. You have a choice of value and reference semantics with sensible defaults. So integers, they're cheap to copy around. We do that by value. Arrays and strings, which under the hood are arrays, have shallow copy semantics. They're by reference, and I'll show you more of that in just a second and why it matters and why it's important. We have modules. D compiles an order of magnitude faster than C++, so fast that for every single D project that I've ever used, and granted they're not huge, but they're significant, it is faster for me to just send all of the files all at once to the compiler and let it cache those modules than to try and parallelize it on multiple cores or multiple machines with a make file. It's just that fast. It's so fast that for my biggest D programs that I use at work, it compiles and begins executing faster than it takes Python to start up. Wouldn't that be wonderful for C++? It's garbage collected. So at this point, you may groan and say, all right, you lost me. The good news is it's optional in the standard library. You don't need the garbage collector to use almost all of it. And everything else on this list we're just going to talk about in the rest of the presentation, the exception to that being polymorphism, which, like C++, is kind of optional. So the classic intro program to any language. I think on this screen there is exactly one line that is interesting, one line that doesn't have a direct C++ analog. Does anyone see my favorite line? Any guesses to what my favorite line on this screen is? The shebang line, that very first one. D is scriptable. If I set the permissions right on this file, I can compile and run that, again, faster than it would take Python to start. So D is now my total replacement for Python. Here is a simple program. D has a great power to weight ratio, and by that I mean, look at how much white space there is on this screen. But this program does something useful, especially if I change that file to standard in. Take a moment, look at this program, ask yourself, what does this do? And when you think you know what it does, put up a hand. Would anyone like to volunteer their guess as to what it does? Yeah. Absolutely. So what we're going to do here is we're going to read in a file, sort the lines, put it back together, and print it all out. And that reads like a set of ordered instructions. It's very easy for a human to go through and say, first do this, then do that, then do that. The only tricky part of this is the dot array. That's the part I think that might confuse you. So we have this file. We're going to read it by line. Dot array says, create an array, which is more or less like a vector, and put all of those lines into it. So copy all the lines, put them in a vector, sort that, join it back together with new line characters, and print it out. And one of the cool things that's not so obvious from this code is that it is as efficient as it possibly can be in terms of making copies. There are 0 extra copies in this program. That sort happens in place. The join operation is just a view of that data. It does not copy the data and put it together in a big, long string. It's just a way of looking at the data in its original form, but as we're looping through it, as we're iterating over the data, it will just insert a new line character and keep going. So there is constant memory usage here, with the exception of the dot array line that is an explicit ask for a copy to be performed. Other than that, there's nothing else. Maybe I/O buffers, but that's it. And I think that that's pretty special. Now, here's a rewrite of that same program. And I did this just to illustrate one thing, and that is the universal function call syntax. If I have a non-member function sort of an argument, I can always rewrite that as the argument.sort. That is the power that lets me write things as a list of instructions. So I rewrote some of the things here, not all of them. If you're confused by, isn't that a non-member function later on in the talk, this is the magic that makes that all work. So let's look at the C++. I don't like the C++. So for starters, this is kind of complicated. It takes up more of a slide. I think it's harder to read. It's very dense. So just first impressions aren't the best impressions. We have a while getLine loop in there. And one of the tricks about that a beginner might not understand is that move is essential. if I do not include the move, the standard move call, I will copy all of my data. And an interesting anecdote that I believe Chandler put in one of his talks at CPPCon, was that if you're trying to benchmark a program, there's these subtle mistakes you can make, like not calling move, or not passing by const reference, or all these little things that make these tiny little copies all over your program. And if you do that, a profiler isn't going to find that. Because it's not like there's this screamingly obvious, broken, very expensive piece of your code. It's all of your code is equally bad. And so it's hard to find, and it's subtle. And you have to know explicitly to do the efficient thing. Contrast that with D. We explicitly did an expensive thing. In C++, you explicitly do the efficient thing. So sensible defaults are things that show up in modern languages. Now, sort, I think, is straightforward. You might be wondering, what's the deal with this string stream? Well, back in the day, I benchmarked, and I found that it was pretty much always better to buffer your output first, if you have a lot of it, and then print it out, as opposed to using cout in a loop or something like that. So again, not something a beginner is going to know to do. You have to do it. You have to use move again so that we don't incur all these copies. This is complicated. It's easy to get wrong. It's easy to go from a solution like this to one that has many more copies. Now, this solution here, the C++ solution, is equivalently performant, equivalently efficient, let's say. It's probably a better way to put it, to the D code. And when I say that, I don't mean that I've benchmarked. I have not benchmarked. What I'm saying is they make the same number of copies. The difference is, did we have to be, did we have to know to do special things to be that fast? And in D, the answer was no, and in C++, the answer was yes. Now, how does this magic build up? To answer that question, we have to look at the primitives in D. And some of the things that we're going to look at are going to ship to you eventually in C++. Arrays is unfortunately just going to build up to that idea. So arrays in D are more or less vectors. They have a length, you can concatenate them, all these wonderful things. And the great thing about having a length in your most primitive array-like container is that you can't get the heartbleed bug. For those of you that remember that fun security bug, the big problem there is that they wrote OpenSSL in C. And when you use C, you're forced into using things like C strings. And C strings, you separate the data and the length, and because they're separate, they can get out of sync, and when they get out of sync, boom, you have a bug. So we need better primitives. Always ask, why is the length separate? If you see something like that, your head should go, that's not quite right. We'll come back to that idea. Now, arrays have reference semantics. Shallow copies. An array under the hood is two pointers, a pointer to the front, a pointer to the end. And when I use the assignment operator, all I'm copying is those pointers. I'm not looping over the data. It is a O of 1 operation. And you can see if I change my aliased version there, it affects the original. To pay for a copy, I have to ask for a copy. I use .dupe, .duplicate. The last thing I want to talk about before we move on is something called slicing. Some other languages have this. What it is, it's saying, I want to change my view of the data. I'm not going to move the data in memory. I'm going to take those pointers and adjust them. So in this case, I'm getting the slice from index 1 to the end. $ is shorthand for array.length. So I have my view of the full data. I chop the first thing off. That is my slice. So let's write an algorithm. Let's write our first D algorithm. And to start, I want to focus on the unit test block at the end there. Now again, you can see that I can write a non-member syntax or a member syntax. It's equivalent. You might be wondering, what am I returning and why? So this is a linear search. I think that there are basically 4 questions you might want to answer from a linear search. The first of which is the thing I'm looking for in the stuff I'm looking through? Is the needle in the haystack? And to answer that question, let me first tell you what we've got here. So I am returning everything from the element that we were looking for to the end of the original array. So I'm getting you a slice from the element we found to the end. And if all we want to know is, did you find it? All we need to know is it the empty slice? So if when we look for 2, we have a non-empty slice, starting at 2, going to the end. And when we search for 0, we find nothing. We get an empty slice out. The second question I think you might want to know from a linear search is Great, we found it. Let me now call a method on it. Let me get a different data member out if it's something like an object as opposed to an integer. So again, that's easy. I can just index the first thing off of my slice, do whatever I want with it. You might want to know everything that comes after, easily given by the result here. I can slice off what we found, and now I have everything that's left. And if I want to know everything that came before that, again, there's some slicing and math you can do to get that. So I get 4 answers for the price of my return type being a little not straightforward. Now, how do we produce this result? What is the algorithm? How are we implementing this function? Well, first off, notice that it is a templated function. We will accept any kind of array. And templates in D are specified with a second set of parentheses. It turns out that it's easier for both humans and compiler vendors to do matching on parentheses as opposed to the less than greater than stuff that we've got in C++. So great, we have this type T, that's our template type. Now the loop reads like this. While there's still stuff to search through, and we haven't found what we're looking for, slice off the first thing and keep going. Now, to make that more clear, if I break this down, if the length was 0, if we had an empty slice, if that was what haystack was, it was an empty array, then we would just return, and again, that would tell us we didn't find it. If we found the needle, then the needle's at the front of the haystack, and I can just return that, and again, that is my answer. And otherwise, we can chop off the first thing and try again. So that's how the algorithm works. This is our first D algorithm. By the way, one does not fail to write unit tests in D. Unit test is a keyword, and this is kind of interesting. So, show of hands, how many of you would say that more than 10% of your code base is tested? More than 20, keep your hands up. More than 40? More than 60? More than 80? Congratulations to those of you who still have your hands up. I don't see that many. So in D, I would say we have an above average number of tests. And the reason we do it is because it is built into the culture. It is built into the language. If you want people to do something, make it a keyword. Now, moving on. I want to generalize my function. I want this to work with not just arrays because it makes sense to be able to linear search over other things. And so in order to do that, we need to break down what these 3 operations are. I need a name for them. So for the first one, for haystack.length is greater than 0, what might be a general way of expressing that idea, of saying, is there still stuff? Shout it out, ideas. Maybe I'll actually ask for a hand. There were lots of different suggestions. Yeah. Dot empty, perfect. So there's a name for that. How about the next one, where we subscript 0? So another way we could have done the first operation, the suggestion is we could have casted to bool. Yes. For our next primitive, dot front, look at the first thing. And for the slicing operation, pop front. Get me to the next one. And this might look familiar. There's an analog in C++. These 3 operations have a similar usage. So in C++, instead of dot empty, we have a comparison. You can compare between the iterator you've got and the end. Are we done yet? You have front, which is dereference, and you have pop front, which is increment. So what I'm showing you here is an input range interface, which is equivalent, in some ways, to an input iterator. And we'll come back to ranges and why they're better than iterators in just a little bit, but part of the reason is that they know their length. It's built in. All right, so I generalized my function. I wrote this version that uses these 3 primitives. It turns out an array doesn't have a front method, an empty method, and a pop front method. But I want this function to still work with arrays, not just things that already have those methods. It turns out if I implement these non-member methods, empty, front, pop front, and I pass in an array, that is sufficient for making this generalized version of my function work with arrays again. Does anyone remember the technique that, or the tool that makes this possible? We've already talked about it. Yeah. The generalized function call syntax. So again, any non-member function can be used like a member function. This is pretty great, and the reason it's great is because primitive types, array types, these are built into the language. The boundary is blurred between those types and a type that I can add any method that I want to. So an integer, I can basically add methods to an integer. An array, I can add methods to an array. And I can just use that the same everywhere. And C++ has a version of this that's under consideration. We'll talk more about that at the end. But big idea here is that we're kind of blurring the boundary between things that are given to us by the compiler, things that are given to us by the language, and things that we make for ourselves. So empty. How do I know if an array is empty? Does anyone have a solution for that? We've seen it before, back before we generalized. The length, we check the length. For front, we subscript 0. To pop front, we use a slice. And here is the entire implementation of an input range. The whole thing fits on a slide, easy. And now arrays will again work with our functions. So it works with arrays, and not that you'd want to do a linear search on a red-black tree, but just an example, it does work now with even more things. So let's go a little bit further with our ranges. Let's do one that's lazy. Now, Python has this thing called generators, as do many other languages. And the thing about a generator is, instead of, if I want to get all of the exponents of 2, figuring out what those are and giving them to you in a vector, I can instead say, here's the first one, ask me when you need the next one. And I will lazily compute that next one and give it to you if and only if you ask for it. Now, the advantage of a generator is you don't pay for what you don't use, a wonderful principle, but also that the generator has constant memory. I'm not allocating a full vector of these things. I'm only looking at one of them at a time. So it's cheaper both in runtime because you don't pay for the whole thing unless you actually need it, and it's cheaper in memory. These are the kind of primitives we need in C++, and the ones that we don't have and that we don't see all the time in idiomatic C++. Spoiler alert, they're coming. So I've got this generator of powers. I'll generate powers of 2, I'll generate powers of 3, powers of 5, and I'll use that find algorithm we just wrote to ask, is 512 a power of 2? And one piece of syntax that's maybe not super familiar is I've got the bang character up there twice. The first time you probably are familiar with, that's a negation. The second time is to pass a template argument, a compile time argument. Now at the bottom there I show the optional set of parentheses. When you only have one argument, it's optional. But that symmetry between the find function signature, where I had 2 sets of parentheses, and the call site, that's what's going on there. Now why might I want to pass a base at compile time? I'm going to compute powers of 2, and I say 2 is given at compile time. Why would I want that to be given at compile time instead of runtime? What's the advantage there? To answer this question, maybe we have to think about how we're doing it. So exponents are computed by multiplying over and over and over again. I mean, if what I've got is something like 2, something like 4, something like 8, I can just use the shift operation instead. If I tell it the basic compile time, the compiler can say, oh, I know a faster way, and just give you the faster way for free. So you move a thing to compile time, you move information to compile time, you get better results. It's pretty cool. Now, here is again the full implementation of an input range. I have empty. Empty just says, are we going to overflow a long? I won't go into the math. I store the initial value. So the initial value is 2 to the 0, 3 to the 0, base to the 0. It's always 1. To get the current power, I use front. To get the next one, I compute the next one with pop front. Again, a full input range right here on a slide. And by the way, if I want a template constraint, this is kind of like concepts. Something that says, hey, no, you shouldn't call me with that. I can use any arbitrary compile time if statement to say, base of 0 is not allowed because I have an infinite loop and divide by 0. We've implemented 2 ranges. I've shown you an algorithm. I've showed you a generator. Why do we like ranges? Well, one argument, perhaps a simplistic one, is they're just convenient. Sort of one argument instead of sort of 2 arguments. I like that a little bit better. But the left-hand side there, the C++ has something else going on. I'm passing a data, some data, and a length. 2 arguments. And this should remind us of something terrible. C-strings, heartbleed, bugs. I don't know if you've written this, but you can. You can have 2 different vectors and pass iterators to each of them. One from the first vector, one to the second. That'll compile. It'll make you very unhappy. I've got 4 bugs, 4 lines here, 4 uses of copy. Every single one of them is broken. And let's focus on the C++, because I think that'll be easier for you all to find the bug in. I'm going to copy the 3, 2, 1, 5, 4 from V into out. That's my goal. And something here is broken. Every single one of those uses of copy. Does anyone see the bug? Back considerer is missing. So what that means is the out vector is empty. There's no space to copy things. I can either use a back inserter to grow it as we go. I can call .resize ahead of time if I know how much I need. But either way, this is a problem. Now you might wonder, why am I showing you code that's buggy in 2 languages? What would be the point of that? Well, in D, we can give you better diagnostics. So in debug mode, because a range knows how much more data there is, because it knows whether or not it's off the bounds, in debug modes, it can just have a little extra if statement and tell you, you have made an error. There's no more undefined behavior, hoping you're not overwriting something important. Maybe you're going to crash, maybe you're not going to crash. In D, we just would abort the program for free. You don't need ascend, you don't need valgrind, you don't need any of these tools that tell you it's just free in debug mode. It gets compiled away in release mode. And yes, there are some versions of C++ iterators, special versions, that have this power too. But one of the issues that shows up if you do that is that it changes the sizes of your iterators, because now they need to know the bounds. Ranges already know. So that's kind of cool. But we can get more compelling. If I want to reverse the way I'm looking at the data, I'm not making a copy of the data, I'm just saying look at it the other way around. I can use a range modifier. I can say array.retro. Sure, C++ has this too. Sort things in reverse order, fine. What if I want to filter? What if I just want the even numbers from my input? Well, I can use .filter, and the way that this lambda function, that's what that is, reads is for each a, if a cleanly divides by 2, keep the element. And the cool thing is that this is lazy. It has O of 1 storage. We're not allocating a copy. If you want a copy, you can ask for it. You can say .array, make me a new array that contains the result. But otherwise, it will just compute it on the fly as you're iterating through. It'll skip the elements as it goes. In C++, there is no idiomatic way to do this in C++ 14. There might be something in Boost. You can probably pull in Eric Niebler's ranges proposal. But in standard C++, you have to make a copy. So I can make a vector. I can use copy if. That's an allocation and a copy of all the things inside. Back inserter, because I might not know how big my vector needs to be until it's all done. And again, my lambda. So it's more wordy, it's more copies, it's more allocations. And ranges compose very nicely. So in D, I can use basically as many lines as I want. That's constant memory. My goal here is to take the string hello world, reverse hello, and put it back together with the original string world. So that's what we're going to get at the bottom. I can slice off hello, put it backwards, slice off world, keep it the same, and chain them together so that they just follow each other. And again, constant storage. This is just a way of looking at the data. We're not allocating new data, we're just looking at it differently. And I can do this as many times as I want. I can retro, I can chain, I can filter, I can map from one thing to another. All of these operations happen without any copies. In C++, the best thing I could come up with in C++ 14 is I make a new string, so there's an allocation. I use those reverse iterators, and I append on the rest of the characters. So I'm copying, I'm allocating all of these awful things all over again. So why ranges? Well, they're safer. Again, no heartbleed. They're convenient. They're memory efficient. One of the reasons why they're memory efficient is because they are lazy, and they do this constant time memory thing. It's very difficult to get that in C++ right now. But another reason is the whole, if I've got 2 iterators, I might have, not just where I am, but some extra metadata, like a pointer back into a standard map. And if I've got 2 of those iterators, I've got twice the metadata. So now if I've got a range, I have half as much. So there's a simple memory benefit there as well. and modifiers are so much easier to write. Why do we not have range modifiers in C++? Does anyone have a guess why we don't have all this laziness, all this kind of delayed computation memory benefit that we like so much? Why doesn't C++ have this today? Readily available, easy to use. Anyone have a theory? I've got one. It's this. To implement an input iterator, you have to implement all of that. To implement an input range is 3 functions. We've seen that twice in slides. Show of hands, who thinks they can correctly implement an input iterator right here now without consulting the internet? Show of hands. I think I see less than 10. Keep those hands up if you know the difference between an input iterator and a forward iterator. Yeah, so it's challenging. It's hard. Boost has things that makes this better, but it's not easy. I struggle to implement iterators in C++, and so creating these modifiers is not an easy thing to do. Ranges, you've got a lot less to deal with. The job is an easier one. So let's go back to talking about exponents. And I want to do something a little different. Instead of generating all of the exponents of 2, I want to ask for one in particular. So 2 to the power of 3. So I can do the same non-member function, call it like a member. So I've basically given a method to an integer. Again, that boundary between primitives and proper objects has blurred. 3 of these lines are the same. The last one is different. What makes that last line so cool? What's the cool thing about that being in a static assert? It's at compile time. I heard it. So I can just use that at compile time. And I'll show you the D version in a minute. But let's ask, why might I want to do that? Why might I want to compute that at compile time? Well, maybe you've got some research that says a particular power of 2 minus 1 is a great initial hash table size. I could code that in as a magic number, and that'd be fine, but then I probably want to comment. Or I can just show how I got there. And I'll give you more compelling reasons why moving computations to compile time, like when we had our base automatically just convert into a shift operation instead of a multiply earlier, is such a good thing. But for starters, let's do this in C++. So C++ 98, the static assertion looks a little different. No longer do we have a pretty function call. It's pow, pass some template arguments, colon, colon, value the stuff out, see that it's correct. And the implementation, the only way you could do this in C++ 98 was with template recursion. This was an abuse of the template language system. I'll start at the middle. That's the base case. It's a partial template specialization. It says for any base, if the exponent is 0, then the value is 1. That is the result. So 2 to the 0 is 1, 3 to the 0 is 1, all of them. And then we have the recursive case up top. It says, grab the previous result, multiply it by the base. That is the new result. If you don't understand this, good. You shouldn't have to. The C++ committee smiled upon us in 2011, and they gave us constexpr. Constexpr is this wonderful keyword that says my function may be evaluated at compile time. Doesn't have to. You can use it at runtime too, but you're allowed to use it at compile time. So here is a much more straightforward recursive definition. It looks like a function. We can actually use it that way. And this is significantly better. This is a huge step up. There's some kind of weird things, though, with C++ 11 constexpr. One of those is that if I wanted to make that ternary operation into an if statement, that'd be illegal. That was illegal in C++ 11. Well, again, the committee smiled upon us, and they said, you know what, we can relax a little. You can have loops, you can have if statements, you can have local data in your functions. It's almost like purity, functional purity. That's what constexpr means to me these days. So I can have an iterative solution here. One of the nice things about being able to have an iterative solution is that constexpr means that it can work at compile time. It doesn't have to work at compile time. So if I can write an iterative solution, one that performs better at runtime, then great. I can have the same code for both compile time and runtime, and it's fast in both cases. Now it turns out this solution is not terrible at compile time. In fact, both Clang and GCC memoize. So for Fibonacci, for example, that's going to actually be much nicer, I think, than if you were to use the same code at runtime. But in general, I like the iterative form. And I like not having restrictions, to just be able to do whatever it is that I want to do. And that brings me to D. Here's POW. This is the same one that I showed you before we went down this road with C++98. It's just a normal function. It's templated. It does the same exact thing as the C++ on the last slide. The difference is there's no const per keyword. Almost anything you write in D will just work at compile time. That's the future. No const expr, just if it'll work, do it. If you use it in a compile time context, do it at compile time. And to illustrate that point, I can use that power generator we wrote. I can use the find, actually I don't use the find, I can use drop exactly, which is an algorithm in the standard library that says ignore the first exponent things in this cases, and grab something out. So almost anything you want to do, you can just do it at compile time. So let's get more exciting. Let's talk operator overloading. Well, at the bottom there you can see I've got both plus and multiply. And I could do subtraction. I could do subtraction and division. All of these things at the bottom, I do that with a single function overload. And the cool thing going on there is I pass a string that is the symbol of the operator, the plus, the multiply, the subtraction, at compile time. And then, of course, the right-hand side. And I can, at compile time, put together a string. I can concatenate a string together with that operator to say this is the code that I would like to have happen. And mixin is built into the language code generation. It's, you give me a compile time string, I will compile it immediately and insert it right here. And that's pretty special. So you might ask yourself, well, isn't that a lot like eval? Isn't eval awful? Eval from JavaScript or PHP, I forget which one of them. The thing about eval is that you often use that with user input, and you do it at runtime. Mixin happens at compile time where your attackers can't find you, and if they can, you've got bigger problems. So CodeGen, built into the language, you can construct any string you want at compile time, because every function works at compile time, and turn it into code. Now, if you don't think that that's cool, prepare yourselves, because here's where things get really interesting. I've got two different ways of generating a regex. Same pattern, same interface, they work exactly the same. Those two lines with auto are very subtly different. Does anyone see why one of them is more cool than the other? One of them's at compile time. Now, we are passing the pattern at compile time. And I don't know about you, I've never written a program where the pattern has varied at runtime. The only program I can even think of that does that is grep. Grep, you're given the pattern and then you do the searching. Everything else, you know the pattern ahead of time. Now, the cool thing about having the pattern ahead of time is most regex implementations, they've got this general purpose finite automata. It has to accept anything and it has to be fast with everything. If I know the pattern at compile time, I can generate a specific finite automata for your pattern and your pattern only. I can be smart about how I do that. And then once I'm done being clever, that code that I've just generated goes to the compiler, and more importantly, the optimizer. So that optimizer that all of those compiler gurus have spent hours and hours of engineering on making your code fast now makes your patterns, your finite automatas, that much faster. So imagine bringing the entire optimizer to bear on your pattern. That's what D does. And in 2014, Dimitri gave a presentation at DConf where we benchmarked our static compile time version of regex against everything else. And it was significantly faster. We had the fastest regex in the world. Why? Because we had an unfair advantage. If you look at the runtime version, it's okay. It's fine. We do not have the best people for regex in the world in the D community. What we have is the ability to do anything we want at compile time and optimize that to no end. Now, there's one more thing I want to show that I just think is kind of nice. And that is, I've got this phone book, a way of going from names to phone numbers, and I'm storing it in a red-black tree, so think a standard map. And I'm going to loop over it in order, print everything out. These are the three things that I think are cool. That first one is just shorthand for a lambda. A mixin converts a string into a lambda. I can have my code be that much cleaner. But what really makes me happy is those last two boxes. that when I'm looping over my red-black tree, I can refer to the things inside with self-documenting names. Compare to the C++. Entry.first, entry.second. Does this bother anyone else in the room? I hope it does. It really makes me very sad. Because it couldn't even have been key value. No, we got first and we got second. All right, I want to give some credits, and then I want to wrap up and talk about what we've done. And more importantly, because you might be wondering at this point, why am I talking about D? This is a C++ conference. I want to relate that all back. So for starters, the first 3 links here are works of Andrei Alexandrescu. He was my mentor for a while, and he is, of course, big in the D community. That first book I want to really talk about, because that is my favorite programming book of all time, the D programming language book. And it's not just because I like the language, but it's because Andrei explains exactly why everything happened in D. It explains the pitfalls of C++ and the design decisions that went into making D the language it is today. It's a little out of date, the book, but it's still a wonderful read, would recommend. That last link there is just the dconf presentation for those benchmarks. And with that, let's wrap up. So things in modern languages and modern compilers were getting more natural and expressive code, where it's hard to do inefficient things and easier to do the right things. You don't have to remember to do move. You can just do what you need to do, and the algorithms will be lazy, they'll be cheap, they'll be constant memory by default. Things are memory efficient, things are fast. We've got work that is moving to compile time, and then we can use the optimizer to do clever things. We can make our code better by just shifting more things to compile time. We've got safer primitives. And what's more, a beginner is less likely to introduce these awful bugs of from C to C++, maybe not freeing the resources, but in D, the difference between D and C++, a lot of times comes down to perf, be that memory or runtime or both. So let's compare things that are coming from D to C++. D's been around for a while. There's a lot of implementation experience. A lot of the proposals, the big ones that are coming to C++, have been influenced by the work done in D. Ranges is a huge one. Eric Niebler went through D, looked at those ranges, heavily influenced the design for C++. We've got shallow copy by default semantics for arrays in D. And that's not coming to C++ because, let's face it, you can't change defaults. But there hasn't even been a clean alternative, or even an unclean one in C++. It was very difficult to do something like my example from before, where I reversed the word hello in hello world. I had to make a copy. In C++ 17, we get an answer to that, and that is string view, a view of the data. Right? That concept that I've been repeating over and over and over again is finally coming to C++. We can look at the data without making a copy of it with string view and array view. We have ranges that are coming presumably in C++ 20. That will let us take those views and do things with them. We'll be able to compose, we'll be able to reverse them, we'll be able to chain them back together, we'll be able to filter. All of these things lazy, constant memory. Universal function call syntax, that hey, I write a non-member function, and I can use it like it's a member function. That might also someday come to C++. Interestingly, though, they want to do the opposite. So instead of any non-member function can be used like a member function, it's if I've got a vector with .begin, I can call that as begin of the vector without having to have a special non-member form of that. That might show up soon. And all of these other things are examples of things that exist today in C++ that came in part from D. I don't want to say that they were directly copied from, but there are influences, modern trends. And with that, I'm Mark Isaacson. You can find this and my other talks on my blog. Thank you.
Yeah, hi. Thanks for the great talk. First of all, I would like to point out that I think you a little bit cheated in the comparison between D and C++, making a pair instead of a struct.
Sure.
So that you're showing off like D is a better one. And the second one, I would like to ask about the slices. How do they work? Like, are they like views, or so that they only are like a pair of begin and end iterators, and they just reference the original data back there, or is it a copy?
Yeah, so the question is, how do slices work under the hood? So if you remember, an array is 2 pointers. So you have the pointer to the beginning of the array and a pointer to the end of the array. And when I'm talking about a slice, I'm saying, okay, I'm going to have two different pointers to a different subset of that original array. So I'm not copying the data, I'm just looking at it with a different set of pointers. So if I want to slice off the first thing, I just have a different pointer that it skips that first element.
Hi, I have two little questions. The first one is, do you use the language in your daily job? If yes, to what kind of task?
Yeah, so I do use D. I use D at Facebook, and I use it for a few different things. So we had some bigger projects. We actually had a C++ linter written in D. We had our C++ preprocessor for a while was written in D. We've retired those projects, though, and we've got a few more that are still going. I use D a lot. Basically, anytime you would normally reach for Python, I reach for D. So I use it for all kinds of different scripting tasks, and one of those tasks is a tool that lets me find reviewers for my diffs. So I can use all kinds of source control data and who builds this and who deploys the binaries kind of stuff using a D script to figure that all out and give me reviewers. That's how I tend to use it in my daily life. I'm hoping that eventually it will make sense for some other tasks as well. There's a lot of cool work in the D community right now to make it so that you can just use it together seamlessly with C++. And when I say that, I should say that the C++ integration story today is actually very, very good. What I'm talking about more is we might eventually get to the point where vector could just be used transparently from one language to the other, which I think would be amazing. One thing that D can do that no other language can do right now is it can catch C++ exceptions. So that's kind of cool.
So I noticed that when there was functions like reverse or joiner or something like that, you omitted the parentheses on method calls, but when you use pop first, there were empty parentheses.
Yeah.
Is that required, and why?
Yeah, so I'm not going to go back to the slide because it's way at the beginning, but the question is, when I had my range, I sometimes omitted parentheses when I did things. So when I did array.front, I didn't have parentheses. When I did array.popFront, I did use parentheses. The answer is that stylistic or mandatory, or what's the explanation there? And it's just stylistic. You don't have to put the parentheses if there's no arguments. I sometimes choose to and sometimes choose not to with really no good reason. Good question.
Your find in D returns a sequence or a range.
Yes.
And usually when you use find, you want to find an element, just one.
Yes.
And sometimes you want to, I don't know, iterate from the first one to the one you found. And how would you do this?
Yeah, so the observation was that for the find algorithm, we returned the slice from the thing we found to the end. And usually maybe we just want to have the thing itself, the thing we were looking for, and how would we iterate from the beginning to that at that point. So this goes back to that the return value can be used in lots of different ways. So if you just want the thing itself, the thing that you found, when you got back that slice, that answer, that's in the array version just another array. And I can subscript out the 0 index, and that is the result. Or if it's a range, I can do .front, and that is the thing that we wanted to find. If I instead wanted to loop up until that point, or get a slice that was all of the things up until that point, I can construct a slice by saying the array sliced from 0 to you can do some math on the length of the original range or array minus the length of the slice that you got out. It's kind of complicated, but it works. Alternatively, you could write a loop.
Okay, one more thing. That t.init, if I'm not mistaken, it
Yes.
initializes to 0, yes?
Yes. So t.init just says get the default initial value for that type. So if it's an integer, that'll be 0. If it's an object, it'll be the default constructor.
So this power will always return 0, yes?
The question was, yes, would this code always return 0? The answer is yes, I have a bug.
All right.
Thank you. Always appreciate that. And the funny thing is I fixed this to say t.init prior to this presentation. So thank you.
Are slices garbage collected? Or?
Are slices garbage collected? So yeah, by default, when you do stuff like slicing, that does get garbage collected. There are some other primitives that you could write to do the same thing without having it be garbage collected. So for example, I wanted to have D arrays in C++, or more just to see if you could, to see if it would be possible to implement the same semantics in C++. And I wrote a library that did that, and under the hood it used shared pointer to do so. So that's shared pointer is kind of garbage collecting, and of course there's all kinds of evils that go along with using shared pointer, but you do need some amount of magic to make that work the way it does.
I can see you have used t.init over there, and does it mean that every single type has a default constructor, or can this line fail?
Yeah, so does t.init mean that every single type has a default constructor? All of the primitive types do, some sort of built-in definition for that. And you can disable the default constructor for everything else, but by default, I believe it comes with one.
So I want to ask, when you play with renders, like you filter something, then you reverse it, and then do some more filtering or something like that. Does the reverse operation make a copy of the range?
Yeah, so the question is, if I filter something, can I then reverse it, filter it more, reverse it, and so on and so forth? And if I do so, does it make a copy? Yes, you can just keep going for as long as you want, and no, there are no copies that are made unless you explicitly ask for them by using something like .array. And with that, I think we'll end questions. If you've got more, come see me afterwards. Thanks again.
Mark Isaacson, ladies and gentlemen.